Achtung, gleich kommt er. Ich gerade rum. Jetzt wieder durch.
Loslegen. Okay. Nochmal eingucken, den Pinsel und dann so, als wenn du das machen willst.
Hast du das nicht? Kann ich das auf die andere Seite?
before any of those 9 days are even a gleam in the construction and testing crew's eyes. However, a plane first needs to be designed and made for the first time. The design and planning process can take 4 whole years from initial conception to the time when the first planes start to be built. To begin with, engineers draw up blueprints and make calculations, which are then fed into equations. Well, once upon a time engineers would have handled all of this themselves. Today flight teams make use of specialized computers to draw, plan, and model the design stage. Following these initial drawings comes the simulation phase. At this point, the team again uses computers to simulate an aircraft's performance based on their calculations and those aforementioned equations. Some of these equations are highly focused. For example, a certain equation, calculation, and simulation sequence can focus solely on the effect of wind upon the plane. Wind tunnels are also used in conjunction with miniature models of the plane to start getting a feel for it. Next comes the construction phase. It is during this point that all of the components described above are first designed and created. The design process will have led to these components either being sketched out from scratch or being selected for compatibility from previously existing models. One thing to note about the construction phase is that it typically involves components from many different companies. Even large-scale companies such as Boeing often buy some of their parts from other companies that specialize in creating a certain type of airplane part. Now it's time to start putting things together, which brings us full circle to the assembly phase. With the designs made reality and the plane's component parts constructed or purchased, it's time to start making the plane itself. Before things get to that 9-day cycle, of course, prototypes have to be built and inspected for quality. It is of the utmost importance that these planes be subjected to rigorous screenings, and the same goes for the materials used to make them. Due to its lightweight nature, aluminum is the metal of choice for building planes. That said, this isn't the lightweight aluminum you purchase at the store, but a far more heavy-duty variant. From the first conception and design phases to the final stages of fitting the last components and testing everything out, building a single aircraft, let alone a whole fleet of them, is a complex process. The margin for error is small, but the people behind airplane construction are trained professionals. The next time you fly, think of the immense amount of work that goes into making these modern marvels. Let's begin our look at how airplanes are made by taking a closer look at that 9-day process employed by Boeing manufacturing the 737. Boeing makes use of fuselages and passenger cabins that are made at its assembly plant in Wichita, and then shipped for assembly in Seattle. This points to another key part of the airplane creation process, that it's very much a piecemeal operation. Different components of an aircraft such as the Boeing 737 are built in different locations, and brought together for assembly later. What's more, these first 3 days don't even concern themselves with many of the flight-centric features that you probably think of when you imagine an airplane. Engines, navigation, means of generating and sustaining lift, turning and landing capabilities, none of these are addressed during the first 3 days. Instead, they are spent installing the electricity, plumbing, windows, and other basic components of the cabin and fuselage. This is also the point at which insulation is added. This is incredibly important for keeping the internal conditions on board safe and consistent. Now things finally start to take on a more plane-like shape, as the wings and tail fin are added. It is of the utmost importance that they be attached with care and precision. Even the slightest deviation can lead to disastrous consequences. For that reason, those constructing planes typically use laser guidance technology or similar methods to make sure that the wings and tail are attached with pinpoint accuracy. Now the horizontal stabilizer is installed to help ensure that the plane is able to maintain balance in the air. This is also the start of one of the most persistent and important parts of the plane construction process, testing everything out. This means that a full plane can not only be built in less than 2 weeks, but the functionality tests for keeping this modern marvel in the air are conducted over just 4 to 5 days. Prior to this point, most of the plane's wiring, electrical, and mechanical systems have been centered around features including the onboard lighting and plumbing systems. Now, the wiring for onboard flight control is added and tested. This marks the transition from the previous, home-building phase to the latter, more technical phase. At this point, the floorboards are fully installed, and elements such as the galleys and bathrooms to which those electrical and plumbing setups are to be connected are installed. Now this is also the stage at which the engines are attached. These require their own miniature version of everything that has been discussed so far. They too have their shells and physical components built, and then have electricity and engineering materials added later. By the time they are formally attached to the plane, like the plane itself, they have come a long way. Once the two begin to be connected, still more tests are necessary. It is vital to ensure that the cables, tubes, wiring, and other components of the engine are connected properly, function perfectly, and that all of these are in turn connected to the appropriate systems on the plane. Now the plane is practically finished, and the final tests begin. This means testing some of the most important components of the aircraft, such as the flight deck and the cockpit. The latter in particular is extremely complex, with modern flight computers being intricate systems that require a great deal of testing to ensure that they are working properly and are in optimal condition. This is the end of the line for the plane. This is the point at which the company purchasing the plane inspects it, tests it out themselves and, if they are pleased with how it has been made, take it from the factory to their fleet. It's a long process, and it's amazing that plane assembly teams are able to fit it all into 9 days. Aircraft manufacturers require cost-effective, high-quality, and often highly technical facilities. To address these objectives, this article provides an overview of several key considerations for the design and construction of plants for aircraft and associated components. Everything about an aircraft manufacturing and assembly building must be driven by the manufacturing process, including process flow, process rate, and process requirements. The building must fully support the process, in addition to keeping the weather out. The manufacturing process must be well understood at a macro level by the facility planning and engineering team to ensure that an appropriate building concept is developed that is integrated with manufacturing needs. In addition, individual manufacturing areas within the building must be understood on a finite level to ensure that the facility and infrastructure supports manufacturing efficiently. Following are key considerations related to an assembly building that must be evaluated during planning to establish an appropriate building overall design. The manufacturing process type and style may include flow line, fixed position assembly, parallel assembly, sub-assembly shops, and fishbone assembly, all of which will determine the building's size and layout. Different manufacturing process flows will likely be used for different components or steps within the overall process. Assembly rate and work in process. The assembly rate and work in process determine the total building size. The building's designers and engineers will need to know how many aircraft will be built in a week, a month, or a year, the rate. Also, how many units will be in production at one time, and in how many assembly positions. Methods of assembling components. Methods of assembling components may include bonding, riveting, fasteners, or even welding. These methods determine the necessary support utilities and potential hazards to assembly workers, defining which safety features will need to be incorporated into the building design. Sizes of components. Sizes of major components including wings, vertical stabilizers, engines, main body, and wing joint components are critical. These determine the overall size of the facility necessary to accommodate the various components, as well as the types of doors, their speed, and staging space requirements. Manufacturing tooling, fixtures, and jigs. Manufacturing tooling, fixtures, and jigs are directly related to the manufacturing process, space requirements, and utilities. Determining how components move into the tooling or whether the tooling moves to meet components are critical issues. If tooling is parked out of the way during Producing a modern aircraft can be compared to leading an orchestra, albeit one that involves thousands of participants with a reach that spans the globe. When all elements are in harmony, the synchronization results in a system that flows and assembles the millions of pieces of our aircraft seamlessly, while giving flexibility and agility to adjust production output in response to market demand. Each Airbus jetliner built today results from proven expertise, accumulated during the company's 50-plus years of leadership, and constant dedication and attention from all teams. Processes are continually refined and make best use of latest technologies and best practices, keeping safety and quality at the top of our priorities. Orchestrating the industrial flow at Airbus relies on 4 contributors, beginning with manufacturing engineering, which co-designs the industrial system in close coordination with engineering, and delivers solutions to the company's various manufacturing functions. The planning, transportation and logistics teams are focused on designing and deploying integrated standards and solutions, with the goals of maximizing efficiency, while minimizing environmental impact. They take care that all pieces, parts, components are where they should be when they should be, and that the aircraft flows through our system smoothly and predictably. Quality is another critical element, with teams ensuring production at Airbus is compliant with industry norms, and its aircraft meet the strict standards established by international airworthiness authorities. They assess and safeguard operations, keeping the company culture focused on safety, quality and compliance. The 4th element involves strategic sourcing and the supply of goods and services. As partners and suppliers are considered an important part of Airbus' extended family, the company's teams are ready to work with them in innovating and identifying areas for improvement, ensuring that the aircraft takes good shape months before its pieces enter our factories. Airbus has more than 20 manufacturing sites, each producing and/or assembling different parts of the aircraft, which subsequently are shipped to final assembly lines where the complete aircraft takes shape. These plants rely on thousands of suppliers worldwide, who produce roughly 80% of the aircraft before it enters our premises. Some plants focus on the manufacturing of elementary parts or so-called metallic or composite detail parts, tubes, pipes, panels, floors, shells, which are used in large quantities in an aircraft. Others focus on specific functional parts and produce elements that include flaps, slats, and other high-lift devices for the wings, horizontal tailplanes and rudders, and pylons that connect and support jet engines on the aircraft's wings. All these elementary pieces or components find their way to designated plants where large sections of the aircraft are being put together and equipped with relevant material and systems for electricity, fluids, air, etc. The assembly of these major airframe components divides the aircraft in 5 sections: the nose, the forward section, the center fuselage, the rear section, or aft, and the wings of course. Specific locations produce each of these sections, fully equipped, facilitating their integration when arriving on the final assembly lines. In parallel, cabins, seats and engines also make their way to the final assembly lines. The A350 final assembly line is the greenest ever built by Airbus, with features including natural lighting wherever possible, and a photovoltaic roof that produces the equivalent of 55% of the power needed for the building to function, as well as the recycling of on-site material during its original construction. Hamburg, Germany is home to 4 A320 family final assembly lines. The most recent one is home to new technologies and processes which were developed in close coordination with employees, applying the principles of design thinking. This resulted in a modern and much more efficient working environment, and the Hamburg experience is now being transferred to other Airbus production lines worldwide. A320 family aircraft are also assembled in Tianjin, China, where deliveries are made to Asian Airlines, while Mobile, Alabama, USA, handles the build-up of A320 family and single-aisle A220 aircraft for customers in North America. Airbus has built more than 13,500 commercial aircraft during the company's 50-plus-year history, maintaining a leadership position through a focus on innovation, performance and efficiency. The production of Airbus aircraft benefits from a truly international industrial system, with cooperation across the company's global footprint, partnered with a worldwide supply chain. Airbus has evolved how its airplanes are built. New digital technologies help to deliver on time while maintaining quality, keep flexibility to adjust aircraft production, and reduce the impact of manufacturing activities on the environment for improved sustainability. Looking to the future, Airbus is undertaking a major transformation called Digital Design Manufacturing and Services, responding to the increasingly competitive marketplace, while also preparing for the next generation of aircraft, particularly to meet the company's goal of being the first major manufacturer to offer climate-neutral commercial aircraft by 2035. To achieve this ambition, aircraft manufacturing and assembly is evolving to bring in new processes, tools and jobs for a different way to design and build aircraft, while also offering an improved workspace for employees. With increased modular design and customization capabilities, the next industrial system will leverage higher levels of standardization and commonality of parts and major components, enabling new build-to-stock and build-to-order decoupled approaches. In the factories, teams will benefit from even more digital and connected processes, tools and devices. This will enable just-in-time operations and flexibility to produce and assemble aircraft faster, in a cleaner, more efficient and even safer environment. They will perform activities with more added value, supported by robots and using lighter weight tooling. This ambitious makeover will enable Airbus to adapt production rates more rapidly to meet customer demand, further enhance quality, increase flexibility in the delivery of aircraft, lower the environmental impact by decarbonizing manufacturing activities, and reduce costs. Four concepts will be the drivers for Airbus's industrial system transformation: co-design, digitalization of manufacturing processes and tools, robotics and decarbonization. Co-design is all about designing the new programs at the same time as Airbus designs the industrial system, integrating the needs of manufacturing, and involving the supply chain in this overall process. Digitalization of manufacturing processes and tools will ensure end-to-end data continuity from engineering to manufacturing. This will facilitate data continuity and flow, transparent collaboration, enabling substantial gains in terms of performance and efficiency, lead times, standardization and access to operational information. The increasing use of robotics in Airbus's industrial system will substantially contribute to reduce production costs and increase quality standards. It will also enable teams in the manufacturing areas to concentrate on added value activities, letting robots do the repetitive, difficult or low added value tasks, increasing safety and overall well-being in the manufacturing areas. The industrial systems transformation is also driven by the ambition of Airbus to decarbonize its overall industrial activities, further limiting their impact on the environment. This includes reducing or eliminating harmful materials and chemicals on the shop floors, cutting back on the use of water and energy in manufacturing areas, and increasing the use of 3D printed parts, even with reused materials.
So die jetzt so drauf haben, vielleicht so.
Ja, ja. Super. Ansetzen. Wunderbar.
The wings are one of the most critical parts of any aircraft, giving it the ability to actually lift off the ground. These long metal fins have to be strong enough to tolerate high levels of stress, while also being aerodynamically efficient. Wings are one of the key parts of any aircraft, giving it the ability to take off from the ground and stay in the air. Using thrust from the engines and airflow around them, wings are able to create enough lift to propel the aircraft upwards, the key idea of aerodynamics. In addition to just the metal structure, wings also feature components such as flaps and slats, to further aid with lift. Most aircraft wings are constructed from aerospace-grade aluminum and, more recently, composite materials such as carbon fiber. Both these materials have an extremely high tensile strength, ensuring that wings can sustain far more than any conditions seen during any flight. Composite materials are lighter, which is why most wide-body aircraft, such as the 787 with its curved wings and A350, now favor more composites over aluminum. The wing frame consists of three main components: rear spar, main spar, and ribs. The spars run the length of the wing, while the ribs run across the width. The required systems, like flaps and slats, are fitted into this design and later covered with the white panels we see on the outside. Due to their key function, aircraft manufacturers are always looking for a way to make the wings more useful and efficient. Depending on the plane's weight and size, wing length has to be adjusted while maintaining a high lift-to-drag ratio. However, longer wings also mean more weight and fuel burn. Balancing all of this is not an easy task, but manufacturers have found a way. For example, the upcoming 777 features a new longer wing design to carry more passengers and cargo, and offsets this with a lighter weight design. The trend is certainly towards longer wings in the future. Aside from the metal fins, wings include more technical systems too, such as computer systems and sensors. Notably, manufacturers have to redesign the number and positions of flaps and slats in every new wing. Flaps are the movable parts found at the back of the wing, slats are on the front, allowing pilots to increase or decrease drag depending on the situation. Curved wingtips have also become increasingly popular in recent years, since they reduce drag and fuel burn, making them a popular fixture of new planes, such as the 737 and Airbus. While they may seem like a small change, wingtips can reduce fuel usage by as much as 4 to 5% on flights. Designing the aircraft wing is only the first step of the process, next comes manufacturing. Both Airbus and Boeing have separate factories producing specific parts, which means there are some dedicated facilities to just wings. Airbus currently has a production facility in Broughton, Wales, which makes wings for all Airbus aircraft from the A320 to the A380. Boeing makes most of its wings at its Everett, Washington facility. The wings start from just assembling the metallic frame of spars and ribs, followed by adding the flight systems and aerodynamic components, fuel tanks, engine holders, and finally, the wingtips. All of this happens on an assembly line, where parts are added and tested being shipped to aircraft assembly plants. The wing facilities themselves are massive, considering they have to make wings that over 70 meters long in some cases. Airbus's Broughton facility is over 900,000 square feet, while Boeing's Everett plants are over 1.3 million square feet. These plants make everything from the spars to wiring to assembling the wings themselves. The only thing big enough to carry an aircraft wing is an even biggest aircraft. For this purpose, both Airbus and Boeing have their own dedicated fleet of jumbo freighters, designed to carry oversized parts like wings or fuselage parts. Airbus currently operates a fleet of Beluga planes to transport wings from Broughton to destinations such as Tianjin or Toulouse. Named for their appearance, which looks like a beluga whale, the manufacturer currently operates 5 of the older type and 1 Beluga. Boeing has its own jumbo freighter, known as Dreamlifter, since it carries parts of the 787 Dreamliner. The Dreamlifter is modified from the 747, with 4 currently in service. Boeing uses the plane to transport parts from Everett to Charleston, and from smaller parts makers in Europe and Asia.
Ausschalten. Und dann mal einschalten.
Just as in automotive manufacturing, the aircraft industry uses assembly lines for manufacturing. The production volume is much lower in aircraft, but the idea is the same. In aircraft manufacturing, a series of positions and setbacks are used to indicate the stage of the aircraft assembly. For example, if 16 positions are used to manufacture an aircraft, the 16th position would be the beginning of assembly, starting with either the nose section or wing spar buildups, and the first position would entail the installation of the engines and nacelle assemblies. The nacelle is the streamlined body which houses the engine. Position 0 indicates that the plane is out the door and ready for pre-flight inspection and flight test. Setbacks indicate the stage a subassembly or buildup is within a position. For example, a wing assembly may only encompass one position, but within this position there may be 3 setbacks. Regardless of position or setback, assembly work is constantly ongoing. Even though one position may have more priority than others, other positions are simultaneously assembled, so that both assemblies will be ready for mating at the proper time. The painting and work on the interior of the aircraft, adding seats and cabinets, for example, are done last, as they can vary from aircraft to aircraft. The production of an aircraft relies on the precise and accurate alignment and mating of each one of the major subassemblies. For subassembly production and assembly mating, a series of floor assembly jigs are used. These jigs hold, support, and locate the individual workpieces or subassemblies until they can be riveted, bonded, or bolted in place. Rigidity of the assembly jigs is critical to prevent misalignment, so most of these tools are large and heavy. Some of the jigs are permanently installed, while others are on rollers so they can be moved to the assembly line when needed. The quality of aircraft depends on good design, documentation, and electronic record keeping to meet Federal Aviation Administration regulations and certification requirements. The windshields, wing leading edges, engines and other critical components must meet the Federal Aviation Regulation bird strike requirements before the aircraft is certified for commercial use. Many different forms and checklists are used throughout the manufacturing process to detail the history of each part made. Various laboratory tests and standardized aerospace material specifications have been developed specially for aircraft. To check how well bonded panels have adhered, they are placed in a water tank for ultrasonic testing. Stress testing is used extensively. A section of the aircraft is assembled and then placed in a test fixture, which simulates actual use under varying conditions. Some of the tests are run until the parts fail, to see if the design safety factor is acceptable. Technological change is a major driving force in the evolution of aircraft manufacturing. Many developments underway involve computerized controls and automation, designed to improve economy and quality and lower energy consumption and pollution. More assembly operations, such as riveting, may become completely automated. Smart sensors with predictive abilities involving fuzzy logic and artificial intelligence are becoming more prevalent. Artificial intelligence or fuzzy controls enable the sensors to predict changes needed in the settings due to changes in load or production volume. In addition to these developments, increasing economic and environmental needs will bring further technical refinements to aircraft manufacturing. The manufacturing processes for aircraft are largely paralleled in the production of satellites, their launch vehicles, and missiles. Because minimum weight is critical for all 3 kinds of products, the use of composites has grown such that it can include the entire structure for satellites and smaller missiles. For these vehicles, electronics production plays an increased role in manufacture, accounting for as much as 70% of the total cost. Nevertheless, the small quantity of satellites necessary, even for large constellations and communication systems, limits some of the benefits of volume production, such as reduced costs, although this is not necessarily true of component products that are common to several satellite designs, for example, sensors, instruments, small rocket motors, and communications equipment. The final assembly of complete aircraft usually requires a facility furnished with a network of overhead rails, on which ride heavy lift cranes, capable of moving large portions of vehicles. Facility size is governed by vehicle dimensions. For example, Boeing's plant in Everett, Washington, is the world's largest building by volume, containing some 13.4 million cubic meters, and covering an area of 405,000 square meters. Airbus Industries' final assembly complex in France, although smaller, with 5.3 million cubic meters, is Europe's largest industrial building. Aircraft assembly normally starts with the joining, or mating, of fuselage sub-assemblies that have been craned into a supporting jig or fixture. As the vehicle is assembled, it is moved through a succession of workstations, acquiring additional sub-assemblies and accumulating its onboard systems, ducts, control cables, and other interior plumbing. Light and medium-weight aircraft may be moved on wheeled fixtures. Heavier aircraft are craned. Modern large planes and spacecraft often are moved via an adaptation of the air cushion technique. Highly compressed air is pumped into the assembly fixture supports and escapes downward through holes. The powerful thrust of the escaping air lifts the entire fixture and vehicle assembly several millimeters off the floor, enough to permit movement by tractor or human power. Major assembly steps include the additions of nose and tail sections, wings, engines, and landing gear. On completion of work at the last station, the airplane is rolled out of the assembly plant to the flight line for its production flight test, a process that involves a thorough checkout of specified performance. Critical for all aerospace vehicles, once they are assembled, are the methods for ensuring the quality of the manufacturing and assembly processes. In the case of aircraft, this involves extensive inspections of structural and mechanical items, including functional verification of equipment such as control surfaces and systems, landing gear operation, avionics performance, weapons systems interfaces, and personnel, crew and passenger, environmental conditioning. Helicopters, as a special class of aircraft, receive inspections that incorporate verification of rotor drive systems and associated gear trains. For spacecraft, even greater emphasis is placed on functional verification, including, in most cases, assurance of the performance of all critical operations in thermal vacuum chambers that simulate space. In addition, since most of its operations are not modifiable to a significant extent once a spacecraft is in orbit, those that are automatically programmed or controlled by computers require highly detailed validation. This is preferably carried out with accurate simulations, if not actual use, of the communication and command links that will be used during the space mission.